Imagine you're a synthetic chemist trying to build a complex molecule. You have a nitrile group, that stubborn carbon triple bonded to nitrogen, and you need to transform it into a versatile aldehyde. It sounds straightforward, but nitriles are notoriously stable. If you use a reducer that's too weak, nothing happens. Use one that's too strong, like lithium aluminum hydride, and you'll sail right past the aldehyde, ending up with an amine. So, how do we stop exactly at the halfway point? The answer lies in a clever, elegant transformation known as the Stevin reaction. Developed by Henry Stevin in 1925, this reaction is a masterclass in controlled reduction. Let's look at the overall blueprint. We start with our nitrile, add tin-2-chloride and gaseous hydrochloric acid, and after a bit of water workup, we get our aldehyde. But the real magic happens in the mechanism. Let's visualize the players involved. First, notice the tin. In this reaction, we use tin-2-chloride. Tin is sitting in the +2 oxidation state, but it really wants to be in the +4 state. This desire to lose electrons is what drives the entire process. Watch what happens when we introduce the dry HCl gas. The HCl protonates the nitrogen of the nitrile. As you can see here, by adding that hydrogen to the nitrogen, we've made the carbon-nitrogen triple bond much more thirsty for electrons. It's now highly electrophilic. Now comes the key insight. The tin-2-chloride steps in and donates 2 electrons. Think of this as a strategic strike. As those electrons move in, one of the 3 bonds between the carbon and nitrogen breaks. We call the resulting intermediate an aldimine tin complex. If you look closely at this structure, you'll see something interesting. The carbon is now double bonded to the nitrogen, and it's bonded to a hydrogen from the acid. This is an ine. In many other reactions, this would be an unstable transition state, but here, the tin salt stabilizes it. This is the aha moment of the Stevin reaction. The reason we don't over-reduce is because the ion tin salt precipitates out of the solution. It's literally hiding from any further reaction. Finally, we introduce water. During this hydrolysis step, the water molecule attacks that double bond, replacing the nitrogen group with oxygen. As the nitrogen leaves as an ammonium salt, our final product emerges, the aldehyde. So, why does this matter? While modern labs might use specialized reagents like DIBALH, the Stevin reaction remains a classic because of its incredible specificity. It reminds us that chemistry isn't just about raw power. It's about finding the exact stop sign in a sequence. By using tin as a temporary bodyguard for our intermediate, we can turn a reactive journey into a precision landing. Next time you see a nitrile, don't just see a stable triple bond. See a potential aldehyde waiting for the right pair of electrons to set it free.